Welcome, everyone. It's really a pleasure to introduce Sean Treichler. Sean is, to give a talk here, Sean is a principal researcher at NVIDIA, and I'm sure many of you guys have GPUs. He probably helped design on your computers here. And he's also got his PhD. While at NVIDIA, got his PhD at Stanford with Alex Aiken doing work on programming models for massively parallel systems. And he's done a lot of great things. And one of the things he told me today is that he's really ready with the adrenaline to be here because he tried something new. He drove a car to go from SeaTac to campus, and he had to drive in between two semi-trucks, right? A tiny little car between two semi-trucks. And he could fit his bag in the car, which is a feat for a car to go, right? So anyways, Sean, thank you. Thanks for coming.
OK, thanks. OK, thank you everybody for coming. I've never given a talk in a room like this. So if you're in the back and you want to ask a question, I think you have to stand up and wave your arms so that I can see you. But feel free to, because I like questions. They keep me awake. I've heard this stuff so many times that I tend to fall asleep. But hopefully it'll be interesting to you guys. So I'm going to talk today about Legion. It's a programming model for modern parallel architectures. And the general outline of the talk is, first, I want to talk a little bit about the programming challenges that people have today on these modern architectures. That will, not surprisingly, lead me into a description of the Legion programming model. And then I'm going to spend most of my time today talking about two kind of key, neat ideas from Legion. One is generational events, and the other is some more recent work on dependent partitioning. Then I'll try to close up with some summary and things I'm interested in doing next. So diving right into it, the programming challenges people face today. I think nobody will really want to argue with me that modern computing architectures are getting pretty darn complicated. You're getting further, ever-increasing processor core counts and complex memory hierarchies that you have to deal with in your system. I'm going to make the claim that traditional sequential and SPIMD models for programming these things are increasingly ill-suited due to the heterogeneity of hardware resources and longer and more variable latencies in moving data around the system. And so Legion is designed to address these challenges. We initially focus on supercomputing applications, but that's really because this is where we felt the need was most obvious about 5 years ago 6 years ago when we started this up. We're pretty confident these techniques are applicable to all computing architectures, basically anything that has really compute intensive work to do. So let's talk a little bit more about modern computing architectures, and I'm going to show a couple pictures. And we're talking about supercomputers, so things like Titan. This is, I think, Tianhe 2 in China. And this is a system down in Austin. And so these are all big supercomputers, apart from the flashy lights and the chrome and the gigantic cooling. There's a couple main things that these things have in common. The first one, as I mentioned, is heterogeneity. And heterogeneity comes in a couple different forms here. The most obvious one that people tend to think about is different kinds of processors. So you might have, say, CPUs and GPUs in the same node, or different kinds of CPUs between nodes. But there's another kind of heterogeneity that shows up as well, which is actually just the relative performance. You may have two systems with both CPUs and GPUs, but if one has a 50-50 ratio of processing power and the other has a 10-90 processing power, you treat those two systems very, very differently in terms of how you target them. And so they might as well be different kinds of systems. So in addition to the heterogeneity, these are large distributed systems, and so you have distributed memory to worry about. It's non-uniform. It's not one-to-one with the processors either, so you need to figure out how to place data, how to place computation in these systems. And the thing that makes this pretty hard is that there's ever-growing disparities between the resources in the system. People often talk about computing horsepower measured in flops, floating point operations per second, and everybody agrees that that's growing much faster than the amount of bandwidth they're able to get from their storage. And I'm going to keep tripping on that. But there's also the disparity between the amount of bandwidth available and the latency. It's actually pretty easy to add more memory to a system, but you can't add it all right next to the processor, and so things get farther away. So I'm going to talk a little bit more about these, but I also want to point out that if I characterize interesting and hard-to-use computing architectures in terms of heterogeneity, distributed memory, and these growing disparities, I can toss other kinds of computing architectures in here as well. Pretty much any personal computer these days, even a laptop, has distributed memory and heterogeneity. And even we're looking down in the embedded space. And in fact, actually, heterogeneity here is quite more obvious than the other things. You'll have 5 or 6 different kinds of processors in here. And so, like I said, although we're initially focusing on the supercomputer space, I want to argue that this stuff makes sense for all computing in the future. So let's talk a little bit more about heterogeneity, and I'm going to try to give you a taste of what this looks like. And so I'm going to show you the system architecture for Titan. That was the first picture I showed on the thing. This is currently the number 3 supercomputer in the world. And so if I look at a node, it has a whole bunch of things in it. The first thing it has is about 16 latency optimized cores, think basically CPUs. Right? These are good at running arbitrary code, but they're big and power hungry, so you can't afford too many of them. We stick some memory next to those, but then we also toss in a whole bunch of throughput optimized cores. These are basically good at adding and multiplying, but if you've got lots of adding and multiplying to do, it's great because these things are cheap and they're very, very power efficient. One drawback is they have a pretty small memory associated with them. And if you want these two processors to talk to each other, there's actually this other third memory that you basically have to mediate things through. So once you've got all this memory, now this is one node. Let's do 20,000 of these and hook them up with the highest bandwidth, lowest latency interconnect that we can build. So this is kind of what pretty much any supercomputer looks like these days. It's a bunch of nodes with a bunch of stuff inside them and an interconnect. And the main thing to take away is that there's tons of different components here. Each component has different APIs, or in some cases even different languages for using them. They have different performance models, and if you want to target one of these systems, you need to keep this all in your head. So the way most people program systems these days is variants of what I'm going to call bulk synchronous programming. And I'll say up front that I have a fairly broad definition of this, and if people want to quibble with me afterwards, that's fine. But the main thing I'm going after here is this is the dominant style of parallel programming, and it's based on the idea of data-parallelism. It's based on the idea of doing the same thing on lots of data and using that as a way to use the parallel resources you have available to you. And so in this model, your program is still expressed as a sequence of operations where each operation is basically trying to span the entire machine. So to give a quick code example, here's basically a very simple explicit integrator. Each time step you estimate the derivative, and then you step it forward, you integrate forward by that derivative. And the thing that makes this amenable to running on a big supercomputer and the bulk synchronous style is that these arrays, this x and dx, are huge, right? And think n in the millions or hundreds of millions. And so you have lots of data, and you're going to operate on it in this bulk synchronous style. And so if you think of this as pictorially, let's think of each of the green things here as a processor in the system. The first thing you're going to do is you're going to distribute your x array over the entire system. And then once you've got that, you can now do a distributed computation of this calc derivative using that data, and it will produce the dx array here. And then similarly, we can use the dx array to integrate forward and get the next updated x. And this is often these things are iterative algorithms, and so they'll just keep going and going and going and chunk along, computing a lot of data. Now, the trouble is any kind of interesting computation here doesn't have this nice straightforward flow of data. You're going to have to share data to do anything interesting, and so typically in some but not all of the steps here, you'll have sharing between the different elements in the array. And so different bulk synchronous models differ in the way you launch the work, the way you describe this sharing, the way exactly how synchronous it is, whether it's literally synchronous or just logically synchronous. But this general idea of expressing things as one thing, conceptually one thing being done at a time that spans the entire machine, is kind of the core of the bulk synchronous style. And so there are a number of challenges that come with this on today's architectures. The first one is just having enough data parallelism. So if you did the math quickly on the previous slide, a Titan node has about 10 million processors that you need to keep busy. So right off the bat, if you don't have 10 million, if n isn't 10 million here, you're definitely in trouble. And realistically, you need more than one element per processor to be efficient. So you really want to be in the hundreds of millions or billions of elements in order to be efficient on a system like Titan. One of the other systems coming down the road in the next couple of years is threatening to have 1 billion different processing elements. So now you need hundreds of billions of elements to be efficient this way. A lot of applications just don't have that much data parallelism. The second issue, coming back to the heterogeneity, is if you have heterogeneous processors, they are good at different things. They have different throughputs. And so you can't just evenly divide your work over processors that are two different types. You need to figure out how much work should you put on this kind of processor and how much work should you put on this kind of processor. And what if one particular computation just can't run at all on a given processor? These are all challenges you have to deal with if you're trying to evenly spread your work across the whole system. And then the final one that I want to talk about is latency. These arrows here where you cross, where you have to move data from one part of the system to another, unavoidably have some latency involved in that communication. And if you're not careful, this can be a major problem for modern supercomputers. So to try to quantify that, I'll show you a couple graphs that I like to call the latency gap. The first one is actually a performance graph. This is the performance of these supercomputers over the last couple of years. And you see everybody's favorite Moore's Law curve, just exponential growth over time. We haven't gotten as many data points recently, but the ones that do exist are still trying to stay on this curve. And so people are, one way or another, finding ways to achieve this exponential growth in latency. But the other problem we have is with the performance. The latency is a different story. And so if you look at the latency of some of these systems, these numbers are actually a lot harder to find. You see a very different trend. You see something that looks like improvement, but decreasing improvement over time. And let's see if anybody wants to guess why this might be.
Sorry, before you get to that.
Yes.
What exactly are you measuring?
This is measuring the time for a message to get from one node to one other node in the cluster.
Closest node, furthest node, halfway across?
Probably furthest node. The numbers are poorly reported, so take with a few grains of salt. Yeah, generally one-way latency in the system. So I'll give you a hint. All those systems I showed you in the previous slide were all the size of a room about this big. Speed of light. Right? There's just a fundamental limit on how fast electrons or photons can get from one end of the room to the other end of the room. And it's going to cap you out in the large fraction of a microsecond range. And so although people can innovate on improving latency in the system, as long as these systems are room-sized, they're not going to get any faster than that. So we've got exponentially improving performance. We've got latency that's about to flatten out. And so what happens if we multiply these two things together? Well, we got flops per second times seconds. We're going to get something in the unit of flops. And basically what it is that it's the number of operations you waste every time bulk synchronous communication stops to trade data around the system. And the main point of this graph is to show you a really scary-looking exponential curve where each one of those exchanges right now is wasting on the order of 1 billion potential operations. And now maybe if you're power limited rather than transistor limited, it's not the end of the world because you can sleep while you're doing this. But still, it seems like an awful lot that you're leaving on the table. So bulk synchronous programming models, which I haven't tried to list anyone in particular because there's so many of them, all have different ways of dealing with the latency gap. This is not a new thing, and they have various ways of addressing it. And the fundamental idea is, well, if you're sitting around waiting for data for this thing to show up, go find something else to do. And they have lots of different ways to do that. But the trouble is it's just really hard to do. And the reason it's hard to do is this picture I'd like to show here. And this is basically what you need to do in order to build a performant parallel program on these systems. And what it is basically 6 smaller problems. You need functionally correct code. You need to map it onto the machine. You need to extract the parallelism, do the data transfers, hide latency. Each of these things on their own is not that big a deal. The trouble is they're all tangled up. If I change one of these, it impacts the way all the others need to be expressed. And I'm constantly going around this loop. And so it's not so much you can't get the performance. It just takes you so long that in most cases you actually physically run out of time on your project to get it as tuned as you'd like. So the key idea in Legion is that there's a piece missing from this that can make it all better. And the piece you want to add is compiler and runtime understanding of the data in your application. And our claim is that if you do this, you can get rid of this nasty hairball. And what you do instead is you ask the programmer to just focus on 2 things. Give us functionally correct application code and tell us how you want to map it onto the target machine. If you do these 2 things, a compiler and runtime that understand the data in the application can do all the rest for you. Okay, so we've decoupled the application code and the mapping, and we're going to automate much of the rest of the process. And this is the key idea in Legion. So folks that I was actually here 3 years ago and tried to give a talk on Legion, and I got much too detailed. So I'm going to err on the opposite side this time and be very high level with what Legion actually is and do it in 2 slides so I can talk about the cool pieces of it. So slide number 1, Legion applications. The way you write a Legion application is real simple. First, you do a hierarchical decomposition of your code into tasks and subtasks. Let's just call these functions calling other functions. This shouldn't be too earth-shattering. The next thing we're going to do is a little bit different, though. We're going to do a hierarchical decomposition of your data as well. We're going to have logical regions, which are basically containers of data, and we're going to let the application describe subsets of that, partition it up into pieces and those pieces into pieces, and give us a hierarchical description of the data. And the idea, as you might guess, is we want this to kind of match up with the way the tasks are using it. So the third step is tasks request privileges to modify data. So when you launch a task, you actually say which pieces of data you're going to go access. And what this does is it gives you a machine-agnostic description of your code. Right? So the code has sequential execution semantics, so you get that nice bulk synchronous style, but we've got enough information to extract much more parallelism and to understand when data needs to be moved around the system. So like I said, I can go into much more detail about how Legion actually works and how you program it, and if you'd like me to, I can do that offline, but not enough time for it now. I want to tell you now about what the Legion runtime does. So that was what the application's job is, and I said the runtime's job is to do the other 4 things in that picture. So the way the runtime is going to do this is the first thing it's going to do is it needs to analyze the data usage of the tasks, right? So the program was described in terms of tasks and the data they're using in each task. What we can do is if we look at that usage, we can extract parallelism. If we find that 2 tasks are using disjoint sets of data, they can clearly run in parallel because they don't interact with each other. Whereas if one task writes to data and the next task and another task reads from that data, then there's a producer-consumer dependence between them that we have to respect in our scheduling. Doing this on every individual element you access would be a little bit too, well, it'd be a lot too expensive. So what we're going to do instead is that region tree data structure I showed you on the slide is actually an acceleration structure the runtime uses to do this analysis much more efficiently. Once we've done this analysis, we can construct a logical dependence graph of the tasks in the application. And that takes us on to the second main stage of the runtime, which is now mapping this application onto a target machine. So in Legion, the mapping is done online. Which means you can base it on real-time feedback or data-dependent heuristics or whatever you like. And the way this works is that the runtime doesn't make any decisions. The runtime solicits all the mapping policy decisions from the application or some library that the application is using for that. And so the idea here in Legion is to make sure the application has complete control over what it wants. When you talk in the supercomputing community, quite often the people you're trying to sell your new idea to are people that know exactly how they want their application to run on a system. And if you can't give them what they know to be the best answer, or what they are confident is the best answer, whether or not it actually is the best answer is a different question. But if you can't give them what they want, then you're done. And from my perspective, it's just a more general point, which is that if I can expose complete control to the layer above, then the application author, anybody else has the opportunity to go in there and come up with heuristics and be able to expect to control exactly what happens and come up with better mappings than maybe the runtime would have been able to do on its own, almost certainly. Once we've got these mapping policy decisions, though, they'll be in the form of, I want you to run this task on this processor, or I want the data for this logical region to be in this memory while the task is running. That will necessarily involve some scheduling and some data allocation and data transfers if you want to move data from one memory to another. And the runtime can do this, right? So the runtime can actually augment our task graph with data management and data transfer operations. And what it's going to do, all these operations are done asynchronously by the Legion runtime, and they're composable through what we call events. And this is a key idea in Legion, that basically anything the runtime does is done asynchronously and composed, which means we can have some pieces of the graph constructed in one place and some pieces of the graph constructed in another place, and have them fit together in a way that lets us do as latency tolerant a scheduling of them as possible. So now that we've got this graph that's asynchronous and composable and includes our tasks, but also all of our data movement and allocation, obviously the last thing we need to do is execute that graph. This is actually pretty straightforward. A given operation will become ready when all of its preconditions are satisfied. And this allows us to do dynamic scheduling to adapt to any variations in latency or throughput, right? Since data transfer is one of the things that shows up here, if a given transfer takes a while because the network was congested, well, it's not ready yet. Maybe we can do something else while we're waiting. And I touched on this a little bit earlier, but another important thing here is that there's the mapper is online, so it's important to be able to give online performance feedback to that mapper so it can tune its decisions. And so that's a key part of Legion itself. So, like I said, that was Legion in 2 slides. It's quite a bit more than that. It started out as a 2-person project and is now, I think, 10, 12 people working on it. It's pretty cool. And so I want to show you the block diagram here to kind of show where the pieces I just talked about were, and also tell you what I'm going to talk about for the rest of the talk. So the Legion runtime was doing steps 1 and 2 in that previous slide, and Realm is actually the lower level runtime, was doing step 3, is the thing that was actually executing this asynchronous graph. And so the generational events I'm going to talk about are a feature of Realm. And then the dependent partitioning I'm going to talk about is actually this data model and partitioning thing, which is sort of on the side, but still a key thing. So, any questions so far? No. OK. So I made a big deal about how it was important to be able to compose all the operations the runtime generates using these events. Let me try to quantify that benefit. And to do this, when we originally showed off Legion, we ported a number of applications to Legion and showed how they outperformed the original versions of the applications and how they had good both strong and weak scaling on a number of systems. And so the question we tried to ask here in terms of composable asynchrony is how much of that benefit actually came from this explicit representation of the dependencies between operations. So to do that, we basically hacked up Legion and we modified it so that instead of composing these operations through events, we instead did a more bulk synchronous style thing, which is where you kick something off, and then when you need to, you wait for it to complete before you do the next thing. And we describe these as implicit dependencies because the application is telling you that it needs to wait, but it's not telling you on what operation it's waiting on behalf of. And so in these applications here, switching to an implicit dependency model actually looks basically like a bulk synchronous formulation. So a couple different applications. The most interesting one is this adaptive mesh refinement one. And this one was neat because we had a reference version that worked on multiple nodes. So the MPI version here is the reference. The blue thing here labeled Realm is actually Legion plus the full version of Realm. And so that's the one that outperformed MPI across the board. And then this green one is what happens when we switch it to this bulk synchronous mode. And there's two interesting things to notice here. The first one is that load node counts were still faster. And this is the benefit. This is actually a different benefit. This is the benefit of Legion's ability to do better mappings of the application data onto the system. And basically, we were able to come up with a way to map the data at low node counts. It would just move much less data, and therefore was better than the MPI version. But then at higher node counts, you see that despite that good mapping, we're giving up all of our benefit. And this is basically the latency hiding ability goes away in these systems if you don't have a way of exposing parallel operations through this operation graph. So, like I said, this was the most compelling case. We had another two applications which both showed similar measurable, significant benefits or drawbacks to taking away the composable asynchrony. The trouble with all three of these, though, is they're all mini apps. And the trouble with mini apps that we had with Legion over the work in general is that with a mini app, you can kind of, one person can pick up a mini app, look at it for a couple hours, and know what the right answer is. I can say, oh, this mini app, it's only a couple hundred lines of code. I can think about it. I can get it all in my head, and I can just write down the right answer. And so it's a little bit harder to show the benefits of Legion in that case because somebody, if they know the architecture, can just write down the right answer. And it's not such a problem. So one of the things we tried to do with Legion is we tried to actually take on a full application. And the one we chose was this one called S3D. This is basically direct numerical simulation that models turbulent chemically reactive flows for internal combustion engines and the like. And so this is actually a production code from Sandia, a couple 100,000 lines of Fortran and MPI. And it was one of the 6 codes that was used for acceptance testing on Titan, which meant we had the advantage of having code that had been pretty well tuned for Titan already. So we ported S3D to Legion. We ran it on Titan and a bunch of other systems, and got some pretty nice results. And so this is some scaling results on Titan from 1 up to about 8,000 nodes. And I want to call out 2 different things here. The first one is that load node counts were nearly 4x faster. And there's a number of factors that go into this. One is that the reference code we were using wasn't able to use the GPU well. There was a GPU version of S3D that was done, but it was exactly this thing of massive hand manipulation of code, and this was actually a variant of S3D they hadn't done it for, and nobody wanted to spend the time to do the same thing again for that GPU code. Whereas this one was able to be, you were able to write the code once and have it do CPU or GPU, so we were able to quickly add the new features and target the GPU. That was worth about 2x right there. The other 2x came from actually hiding the latency of CPU to GPU transfers even within a single node. That was important. But the other thing I want to show you here, and I want to claim this is definitely a benefit of composable asynchrony, is the fact that you go up to 8,000 nodes, and despite everything Amdahl's law tells you, our performance improvement actually grows rather than shrinks. So we're nearly 7x faster at high node counts. And this is all down to being able to handle the variability in the network and find work to do when the thing we're most interested in isn't quite ready yet. So hopefully these numbers are big enough that you agree that composable asynchrony is worth something in Legion setting. I'm going to talk about generational events now, and the reason yes?
If you could comment a little bit on the programming effort here, so if you were to compare programming efforts on the MPI Fortran version versus the Legion S3D, how would you?
The programming effort. So the Legion S3D effort took, I think we decided it was about 4 grad student months to actually do the coding. It's a little hard to measure because we were hacking on the runtime at the same time, and some of the things we were hacking on the runtime would have made the things we did earlier better. So if we did it from scratch, I actually think it would be probably no more than 2 months. Legion is a different way of programming than the bulk synchronous style, so it does mean at least your top-level code gets a pretty healthy rewrite. Our goal is that you can reuse the main key computational kernels pretty much untouched. But there is definitely a buy-in to this, right? The Legion benefits from getting this information from the application about what data you're using and how it's decomposed. And the reason we need the programmer to give us that is that that's not the sort of thing you can extract from most codes automatically. But yeah, so it's been a tough sell in some cases, but numbers like this get people's attention pretty well. OK, so I wanted to talk about generational events because I've told you the benefit of composable asynchrony, but I haven't told you what it cost. So let's look at that a little bit. And what I want to point out to you is these event graphs that we're building can get really large. So here's a sample event graph from, I think, the tiniest little mini app, little tutorial app we have in our tree, and it's already smaller than anybody can read. I didn't even try to do one for S3D because it generates 1,000 events per time step per rank. So a 24-hour run, like the scientists tend to do, would be about 100 billion events. And I don't think there's enough pixels to pull that off. So clearly, handling of events, handling of the chaining of operations and the dependencies on each other needs to be very efficient and scalable. And this is complicated by the fact that this is a dynamic runtime, so any event could theoretically be needed anywhere in the system. But most aren't. And so that's the thing we're going to go after to try to make it efficient. The first and most obvious one to go after is anything that stays on a single node. A local event needs to be really fast. And we've benchmarked this at well over 1 million triggers per thread per second. So this is basically fast enough to not be a problem. Like I said, S3 is 1,000 events per second per time step per rank. So it's actually a little bit less than 1,000 per second. So definitely fast enough for that. And the real key is how to do the distributed ones, how to do the ones that cross nodes. So let's talk a little bit about the distributed event implementation. So these realm events are distributed data structures. And our basic event basically has just 2 states. It's either untriggered, the operation it's representing has not finished yet, or it's triggered and the operation has completed and anything dependent on it is ready to go. Event handles need to be able to be freely copied, stored in data structures. So right, the Legion runtime was that block sitting on top of Realm. It's going to take these events and put them in data structures and send them around and do whatever it needs to do. The goal here is that needs to be something it doesn't need to, it needs to not have to check with Realm every time it does that. And because we have this concern for scalability, we need to make sure that storage for an event is only allocated on interested nodes. And my definition of an interested node here is either the node that created the event, the node that's going to trigger the event, or any node that has an operation that's dependent on the event. And in practice, for most events, this tends to be a very small number. You get a couple that have wide fanouts, but usually it's pretty small. However, you will often get many operations on the same node that are dependent on the same event. And so it's important for network bandwidth to aggregate the messages. And so I'll show you, we send no more than 2 messages per interested node per event. So a little pictorial representation. Let's say we have 4 nodes here, A, B, C, and D. And let's say A has some operation that it's running, and it decides it's going to spawn an operation on B. Right? This is going to be sent over the network. It's going to take some time, so we want to have an event handle that describes when it's completed. And so A needs to create an event to describe the completion of this operation. It does this locally on node A, talks to the Realm runtime there, and Realm says, OK, well, let's create an event. We'll call it E1. And the red dotted line here means it's in the untriggered state. And that's great. Now E1 goes back to the operation, and A can send that over to B and say, OK, hey, when you finish this operation, trigger event E1. Asynchronously with that, A can also say, for example, to node C, hey, let's do some other operations which might be dependent on E1. So we'll ship E1 over there. And maybe C starts 3 different operations over here. Each of them is dependent on E1, so they need to say, well, has it triggered yet? And they will perform a query, and again, to the local Realm runtime on node C. C hasn't heard of E1 yet, but it can create the data structure and conservatively mark it in the untriggered state, and then send a subscription message up to node A that says, hey, tell me if E1 has triggered yet, and if not, tell me when it does. Since E1 hasn't triggered yet, there's no response. We don't bother sending a NAC. We'll just send the one trigger message when it has finally triggered. The other operations on C might also do queries, but since we've already sent a subscription, we don't need to send anything else over the network. Maybe eventually B does its thing, and it says, OK, I'm ready to trigger the event. It will send a trigger request to the runtime on B. Again, we haven't seen E1 there, so we'll have to create an object for it. But now we can immediately put it in the triggered state, since this is a trigger operation. and send the trigger message back to the owner, node A. It can update, and then it knows that node C has subscribed, so we'll send that there and forward it to these guys, and now everybody has heard that E1 is triggered. Now, one thing that happens quite often in Legion applications or anything built on this model is that now sometime much later, some operation on D may come along and say, hey, I'm dependent on E1, I think. Tell me the state of it. The event has triggered, but node D doesn't know that, so it again creates it in the untriggered state and sends its subscription message. But in this case, we can immediately respond with a trigger message and notify this guy relatively quickly. So there's no attempt to broadcast the event out to everybody saying it's triggered. We wait until somebody comes and asks for it. And there's a key idea here that is kind of a neat artifact of building a runtime that's latency tolerant, is that sometimes you're willing to actually increase latency to get something else back for it, right? We could have just broadcast the triggering of E1 to everybody so that we could save time when that operation on D came along, but that would be a lot more messages. And it turns out once you're latency tolerant, maybe the cost of one more round trip over the network is not as big a deal as it is in the bulk synchronous model. So we have a lot of cognitive mismatches with folks in MPI land, for example, with this, because they wonder why why aren't you doing these? You're doing 2 messages, you only need 1, and we explain why, and they say, okay, it makes sense.
Sorry. Would aggregation work as you scale the number of nodes? Would you have to wait longer to be able to aggregate to a certain destination as you have more nodes? The probability goes down that you're going to go to the same destination.
So we rely on the. Usually what happens is when a piece of, usually if a remote node cares about an event, it's because some piece of data is being sent there. And usually it's going to kick off more than one thing. So it's pretty common that you're going to get multiple things on that node that want it. And similarly, unless you have an all-to-all data sharing pattern, it's generally the case that the total number of nodes that are interested in a given event is relatively small. So this fairly simplistic model of one-to-one messages with the owner aggregating locally seems to work. If you had cases where there was a lot of sharing, you might want to be a little bit more aggressive.
Great, okay.
Was there any other questions? Yeah.
When is it okay to get rid of an event?
Have you seen my next slide? So the question was, when is it okay to get rid of an event? And that's exactly what my next slide is about. So a little seeded question there. Okay, yeah. So the question is, how long do these things need to live, right? I made the point that the event, you can get queries of an event much after the original trigger. And so if you're looking at how many events do we need, we can first ask, well, how many events are there total in an application? So what I've got here is a graph of actually a very tiny application. This is the little, folks that have done Parsec, this is actually the Legion version of Fluid Animate. Run on just 16 nodes for not too long. And the total number of dynamic events, so these are the total number of events created, is actually pretty large. If you look at the run rate here, it's about 1,600 events per node per second. So it's pretty clear if I was going to run this for a day, I'd have a few too many events on my hands. So I need to be able to reclaim storage. And when can I do that? Well, certainly, I have to at least wait till after it's triggered. But we also need to wait until all the queries have been performed, since the queries can come much later. And so the question is, how do you do this? Well, all the compiler folks in the room will say, oh, this is live variable analysis. And it is. And so let's assume that we could somehow prune this down to just the number of live events. What we would get is a graph that looks a little bit more reasonable. The run rate here is only 130 events per node per second. So that's not bad. So how would we get this? Well, there's basically 2 ways to limit our resource usage to just the number of live events. The first one is manual management. We can have the application just tell us, oh, I'm done with this event. I'm never going to use it again. Go ahead and delete it. It works reasonably. I mean, it's very efficient, I guess, but the trouble is it's very error-prone. No end of studies of people showing that this is done. Both false positives and false negatives are rampant in code. So the other way people tend to do this is reference counting garbage collection. It absolutely works, but it adds overhead. And when I'm running around with 1,600 events per node per second, it could be kind of scary overhead. The other problem is that I made the point before that we wanted the Legion runtime to be able to take these handles and just do whatever with them. Put them in data structures, toss them around the system, which makes the reference counting actually quite hard to pull off in this model. So we're going to do something different. We're going to do something that ends up actually being better than just live events and also cheaper. And the idea is, the key to it is this notion of generational events. And the key observation is that this one fixed size data structure I was showing you on the previous slide, this event object, can actually do a couple things. It can describe that one untriggered event, but it actually can it can also describe a very large number of already triggered events. And the easiest way to think about this is maybe pictorially. So I've got events here, X, Y, and Z, and their timelines. So they're created at some point, they're triggered at some point, and there's 0 or more queries at different times. And the interesting thing about X, Y, and Z here, and I chose it carefully, is that they're untriggered lifetimes. The time between when they're created and when they're triggered don't overlap, which means that they can all share what we call a generational event, which is this generational event W on the bottom. And the idea here is that when you create a new event, you can actually reuse an existing generational event as long as it's in the triggered state. And so a generational event keeps the triggered versus untriggered bit, but it also keeps a generation count. You can basically just, as soon as the previous generation has triggered, you can layer a new generation on top of it. And you can stack as many as you want because you have the invariant that only the top one can possibly be untriggered. And so, yeah, so as long as it's in a triggered state, and so that becomes the next generation. And so the idea here is that this is a very simple change to the algorithm I showed you before. In fact, I don't need to show you the messaging anymore because it's basically the same. We just pass generation numbers around as well. And so if somebody says, hey, I'm querying generation 1, and the event is already in generation 3, and I have a pointer for this. That's that little guy over there, querying 1 when we're in state 3. We know it's triggered, right? We wouldn't be on generation 3 if generation 1 hadn't triggered. And so if it's for the current generation, we look at the triggered, untriggered bit. And if it's not, we can just say, oh, yeah, it's triggered because we layered a new one on top of it. So, simple trick gets us a really huge benefit. So to show you, to quantify that, let's come back to this graph here. And again, I have the live event graph in blue. And now this green graph here is the total number of generational events we use in this application. And so a couple things jump out. First of all, it's only 20% of the storage of even the most optimal system based on counting live events. So we haven't just reclaimed things when it was safe to. We reclaimed them before it was safe to, which is pretty cool. There's no overhead from the garbage collection, which is pretty awesome. And the other thing that jumps out here is there's no sensitivity to the length of the run, right? It's pretty common, even in a garbage collected system, to have cruft accumulate over time. And the nice thing about the generational event system is because it dynamically reuses these generational events as soon as it's in the triggered state, you basically hit a high watermark that's kind of based on the width of your task graph. And you just sit there for the entire run of the application. So it works out really well. So generational events are cool. They let us do things like 100 billion events in an S3D simulation without collapsing under the weight or running out of memory or anything like that. So any questions on that before I switch to talking about dependent partitioning for a moment? Yeah.
Sorry, one related question is where is the directory for the event stored? Like how did event D know that, or sorry, node D know that event A, or sorry, node A had that event? Okay.
So the question is how did everybody know that E1 was owned by A? How did they know all the messages should go there? And the answer is it's encoded in the handle. We borrow some subset of the bits of the handle to say who is the owner. And that makes it easy to send the messages. It also makes it really easy to assign fresh IDs that aren't going to conflict with anybody because each node can basically keep its own counter. So it's just a namespace, simple namespace partition. Yeah?
That also means it's got to be more difficult to do repartitioning if you decide. So I assume that none of this will work well if you have a distributed system and you have to worry about node failures.
We've thought a fair amount about resilience, and I don't want to go into it now, but I'm happy to talk with you offline about it. The answer is, yeah, these events aren't resilient, but Legion has enough information to basically rebuild structures. So you won't reuse, if an event fails, that's fine. Go get a new event on a different node if you send it there. That was the real quick version. OK, so let's talk about dependent partitioning. So like I said, this is very different from generational events, but comes back to this idea that the key idea in Legion is that we want the application to partition its data, describe decompositions of the data, so that we can expose parallelism, so that we can minimize data movement and get the scalability that we want and the performance portability that we want. So if you're going to do partitioning, I already said it's critical for distributed systems. And if you're going to have language support for it, let's see what the wish list should be. We want it to be very expressive. In particular, I claim you'd want to be able to handle both structured and unstructured data, handle multiple different partitions of the same data. It's pretty common in say, scientific simulations. You want it to be efficient and scalable. You want it to be easy to use, and you want it to be verifiable. And so jumping ahead a little bit, dependent partitioning, the framework I'm going to talk about, is going to offer all of these things. And it's designed to be incorporated into existing languages. So it's a framework rather than a language. Our goal was to make it something that we could reuse. So before I talk about dependent partitioning, let me tell you about the two existing points in the space that people use. The first one is kind of the one extreme of the spectrum, which is basically the very simple cases. So this is common in most of the PGAS languages that do a global view of data across these parallel systems. So Chapel, X10, UPC. I'll show you a little bit of Chapel code here. You basically have X and Y are domains. So think of they describe the extent of arrays, and then my F and G here are arrays that are using X as the domain. And so if I want to partition data across the system, it's really easy in Chapel. You just say I want to domain map this, and you can have block mapping, or you can have cyclic mapping, or you can have block cyclic mapping, and that's about it. So it's really easy to use, and it handles a lot of common cases. So I don't want to belittle it. It's actually quite good for what it does. It has almost no overhead for the cases it handles, and it scales very well. But it only handles those limited sets of cases. And it also has no ability to check the consistency of partitions. So I have two different partitions of the data. It's totally on the programmer to make sure those two things match up. So the other extreme would be full expressivity. And again, I'm not going to try to describe this in words. I'm going to show it in pictures. And what I'm going to show you is the partitioning that's used for the circuit simulation that we commonly show with Legion. And so it's basically a simulation on an irregular graph. And so we have nodes and wires, so nodes and edges in the graph. And let's say we want to partition it up into 3 pieces. And again, we want to expose as much parallelism as possible and minimize the data movement. It turns out if you want to do this, you need a bunch of different partitions. The first one you need is the nodes that are owned by each partition that are kept private to that one. So you never have to communicate them anywhere. Then you need the nodes that are owned by each subgraph that do need to be communicated with other folks. So these are the ones on the boundaries. You also need the nodes that are used by each subgraph that aren't in that one. So these are commonly called ghost nodes, so the ones in the neighboring partitions. You need to know who's going to do computation for each of the wires. And then it turns out you actually want one more thing also, which is you want this middle intermediate partition that distinguishes the private data from the shared data. And this is the thing that lets you, for example, localize all the private data onto the GPU and keep it on there and never move it. And so the goal here is not to defend why you want this. My claim is that if somebody says this is the partition I want, the job of a generic runtime is to say, OK, let's give you that. And if you can't express it, well, that's a knock against you. So it will come as no surprise that Regent, which is the compiled language sitting on top of Legion, and of course Legion can express all of this. It can handle arbitrary unstructured data. It can handle the multiple partitions of the data. It can handle overlapping and alias partitions. But that's basically the only bullet point we got. It uses an opaque coloring object, and so the performance is actually not that great. Luckily, you only partition once at the beginning, but still, you'd rather not spend forever partitioning. And you'd like to be able to perhaps repartition over the course of a computation for load balancing. It's not at all easy to use. That circuit, the code for that was about 159 lines of yucky-looking Regent code. And it cannot be statically verified, right? That's 159 lines of basically opaque code. The compiler can't do anything with it, and the runtime can't verify it except for at fairly significant cost. So we want something like this expressivity, but we need it to be more efficient. And so the way we're going to do this is we're going to look at what's actually going on in this 159 lines of Regent code. So if we stare at it, what we see is actually the code was kind of doing this. First, it figured out, OK, well, what's my original partitioning of the graph? And from that, I can figure out, OK, well, who should work on the wires? And based on the wires, I can then use the connectivity of the wires to figure out, OK, what are the nodes I'm going to access, whether they're mine or somebody else's. The difference of those two things will tell me which are the ghost nodes. Any ghost node is by definition shared, so that's shared versus private. And then I can use that it uses that to basically figure out, OK, well, which are actually the private ones and which are actually the shared ones. So there is some structure here. And we went and looked at the other applications. There was structure there also. And so what we came up with was this idea of the dependent partitioning framework. And it's based around this notion of index spaces and fields. And I'm going to be really vague, abstract here first, because, again, this is trying to be a language-agnostic framework. So we're going to talk about index spaces, which are sets of names of objects. And we're going to talk about fields, which are mappings from objects to values. And to make it more concrete, I'll show you a couple quick examples. So C++, names or pointers, fields or fields. Chapel I already showed you, and then Regent and Legion map all onto this. But all of these can be lowered onto a much more mathematical representation, which is the language of sets and functions. And so we call this DPL, the dependent partitioning language. And once you're in the language of sets and functions, a bunch of neat things happen. A bunch of things fall out. What are the sorts of operations you do on sets and functions? Well, if I've got sets, I can do things like union, intersection, and difference. And if I've got functions, I can do things like filters, set comprehensions. I can do image and pre-image operations. So armed with these things that naturally fall out of thinking of things in terms of functions and sets, I go back to what Circuit was trying to do, and I say, OK, well, that was a filter. That was a pre-image. That's an image, difference, union, and a couple intersections. And so it's a kind of a natural fit for the kinds of things people are doing. And if you think about it, most of these partitioning things are based on topology. Topology is based on walking connectivity forward and backward through things. Database folks might call these joins. But this idea that you can capture a lot of things with this showed up in basically all of our applications. And so again, dependent partitioning is a framework. I'm running a little bit short on time, so I'm gonna do what I can here. So it's a framework designed to be incorporated into existing languages. So the partitioning operations are basically added to the existing host language based on the host language's notion of what index spaces and fields are. They have straightforward implementations. And importantly, we can now, any program that's written using this framework can be lowered into DPL. And I do this by basically abstracting away all the stuff that isn't the partitioning. So all the individual objects go away, the computation of the fields go away, and I just look at the partitioning operations themselves. And I can perform static analysis on this. So we did a proof of concept of this in Regent, but I actually think this would be an attractive, Chapel would be an attractive language to try this out in as well. And so I'm trying to find folks to do that. So quick word about the static analysis. You can have assertions in DPL as well. And these also get lowered and can usually be statically discharged. And if I can do that, it basically guarantees the consistency of the partitions for all possible inputs, which is the thing you're always looking for with static verification. So this over here is the DPL version of Circuit. Don't try to read it. The important thing is that we can take these assertions at the bottom and further lower them into this blob of first-order logic. It's sort of a nasty blob of first-order logic for folks that have played with it. It has nested quantifiers and negation. It has uninterpreted functions and integer arithmetic. All these things are a problem for decidability. And if you have analysis that's not decidable, then it keeps coming back saying, oh, I don't know. It's not so good as an analysis. So we're looking for things to make it more tractable. One of them is it has a property, it's a subset called FO2, which means it has no more than 2 free variables. And this comes from the nesting structure of the existentials that we use. It also has no predicates. And then there's a further structure to the quantified statement, which is sort of hard to give a traditional name to. But it leads to a separation of the predicates you use into simple versus complex. And simple ones are actually most of them. And if you have only simple ones, we show there's a sound and complete algorithm for proving whether this formula is satisfiable and therefore whether your assertion is valid or not. So you get a straight up or down vote on whether your assertion is valid. If it's not, if it's complex, we need to rely on heuristics. And the simple answer there is toss it into an SMT solver. Quite often you get yes or no. But if you don't, you get a runtime test. And the good news is the runtime test is actually a lot more efficient than it was before. Program productivity, I'm going to skip through real fast. Basically, it's one line for each of those arrows there. So you can decide whether lines of code is the way you want to measure productivity. But it's a huge reduction, and it captures the semantics of what you're trying to do rather than opaque code. Performance on a single node. We are comparing against the old partition code in Regent. And so on a number of applications, number of different problem sizes between 2 and 10x faster. And this comes from basically the runtime being able to understand what it's doing and perform these operations in a more efficient way. The orange bars here are when we throw a couple more threads at it, because the runtime now understands it can actually do it in parallel as well, and we get benefits from that. Pretty good strong scaling results as well. Circuit isn't great, but it actually matches the way the application itself scales. One thing I really liked about dependent partitioning was that it let me pull in related work from so many different places. Basically, I got to talk to basically everybody within the Gates building at Stanford, which is pretty cool. So I'm not going to go through these now, but if you're interested in it, we can talk offline. And I think I have, 1 minute left? So real quick, future thoughts, final thoughts and future work. So in summary, the Legion programming model is designed to address the challenges of modern parallel architectures. It contains numerous and often kind of complementary innovations that we're proud of. So I talked today about generational events and dependent partitioning, but get me going and I can talk for days at least on it. It's the foundation for many current research efforts. And then the thing that I'm most interested about now is that I think it opens the door, Legion and things like it open the door to more efficient computing architectures. And so a quick thought on this. I'm going to make the claim, and I expect people to argue with me to some extent on this one. I'm going to claim that the performance of existing systems we have today are primarily limited by the complexity that the human programmers can tolerate. I think there are so many ideas that people have had which don't see the light of day because they're too hard for people to use. The reason is that we tend to treat the layers of software and hardware stack in our computational systems in isolation. And if you only can change one thing at a time, it lets you do a nice apples-to-apples comparison of your idea versus the prior art, but it really limits you in what you can do. And so what you get is these huge efforts to go into evolutionary changes with diminishing returns on existing architectures. So what I'm personally interested in is ignoring most of those and going after what I think are some revolutionary opportunities that exist if you can make coordinated changes across the stack. So just to toss out a couple ideas, you can imagine compiler transformations that rely on some new custom hardware feature that just didn't exist before. Similarly, you could rely on hardware with many custom data paths and accelerators that no human is going to be able to target. You're going to need a compiler and a runtime to do that for you. Dynamic profiling and JIT compilation can allow you to handle data-dependent behavior in ways that you couldn't before. You can also imagine building interconnection networks that are smarter. Maybe some of this scheduling and event management that I was talking about here should actually be in the network layer, since that is the thing that's connecting the nodes in the system anyway. So there's a lot of things to do here. I want to claim that programming models are a key enabler to make this stuff happen. So that's what I've got. Thank you for your attention. And if there are any more questions, I'm happy to take them now. As Lewis falls over on the side here.
Questions? More questions for Sean?
Right. Yeah. So imagine that I have a very fine-grained parallel system. And rather than clumping my tasks together so that they run well, can you give me a rule of thumb on how many instructions I need to put into one task before most of the work is in synchronization agreements and such?
OK, so the question about granularity of tasks. And I'm going to answer it for Legion, and then I'm going to answer it in general. So the answer for Legion is that Legion's sweet spot is around a millisecond to 100 microsecond tasks, so pretty large tasks. But if you think about it, that kind of matches the granularity of data movement around a big system. Right? So if the thing you're trying to help people with is moving data across a network that has microsecond level latencies and operating on chunks of data that are kilobytes and megabytes in size, it's actually an OK trade-off. It's totally not a trade-off, though, if you're doing, say, graph analytics, where your operations are tens of instructions. And the obvious answer there is that you can't tolerate a microsecond of overhead for tens of instructions. And so you need to not pay that overhead at runtime. And so what I imagine there is either some combination of compiler, doing some of these things we're doing currently in the runtime, you could elevate up to the compiler if you can actually analyze it in the code. And some of these things you could imagine moving down into more custom hardware. You could theoretically imagine a little event accelerator on the side of a processor that does some of these things on a much more fine-grained basis. And to be fair, a lot of people have suggested these things in the past. And the question is, how do you target them? Yeah?
Will you be able to handle cases where the data dependency or the data region is not known beforehand? Like complicated patterns like recursive programs.
OK, so the question was handling data-dependent partitioning and recursive cases. So the data-dependent partitioning just falls out naturally because all of the partitions that I showed you in Legion are defined at runtime. So when you load in the data, you can think about your partitions, you can define partitions, you can change your mind and compute new partitions if you want to repartition your data and do different load balancing. And so it's a runtime system, which means we can tolerate that.
I mean, like the cases where like you have pointers and you don't know the dependency beforehand, or which partition you are going to access beforehand.
OK, so if it were truly random, you'd have a problem, right? But if it were truly random, it's hard to do much with that, right? If really you're saying, I might randomly talk to any bit anywhere in the system, well then, yeah, you might talk to any bit anywhere in the system. I'm going to claim that most often you have something where initially you don't know the structure, but if you're willing to take some time and think about the structure and describe the structure to the Legion runtime, then it can accelerate repeated computations on that. So for example, you might load some arbitrary graph in, and you do some partitioning of it. If you then, at that point, do a partitioning like the circuit one I showed you, you could then do iterations on it much more efficiently than if you treat everything as a potentially random access. And recursion is actually just falls out naturally, right? These are hierarchical decompositions where there's no restriction on the depth. So if you want to keep iterating down and either further refining or keep operating on the same chunk, that's totally fine. Good questions.
All right, so I have one final question. So you mentioned extending what you or thinking about more heterogeneous systems with custom hardware potentially for specific applications. Do you have, I mean, a lot of people have been talking about this, especially given that we're seeing, just start with FPGAs everywhere, even in data centers and mobile phones now and so on. Do you have some initial thoughts on how to do that? It sounds like magic to me. You need some more information to make a decision in such a diverse hardware-software interface, how to pick the right one.
Okay, and so I'm not sure you're going to like this answer, but the Legion solution to that is to make it your problem, but to make you productive in solving the problem. Mm-hmm. And what I mean by that is if you're not sure whether something should run on the CPU or the GPU or this FPGA accelerator, you can give me implementations for all three. And you can, literally by flipping a little argument to a call, at runtime try all three and see which one works the best. Mm-hmm. And the nice thing about that is the right answer may be data dependent. It may be time dependent. It may be dependent on what other stuff you're doing in the system at the same time. Mm-hmm. And so basically the idea in Legion is we're not going to decide for you. We're going to give you all the control you want, and we'll handle all the busy work. And so when we say performance portability, we don't mean we're going to magically run well on a given system. We mean that you're going to be able to, we're going to give you the tools to quickly iterate, or the tools to use an auto-tuner to quickly iterate for you to find the ideal mapping.
Okay.
And that is a key difference, which sometimes gets lost in our sales pitch.
All right, got it. All right, let's thank Sean one more time.